Hello, I'm glad to be here at ICASSP 2021 to present our work on small footprint text-independent speaker verification for embedded systems that remain below 240K learning parameters while bringing competitive results on well-known benchmarks. I am Julien Balian, machine learning scientist at SONOS, working with my colleagues and co-authors in the voice experience team, Raffaele Tavarone, Mathieu Poumeyrol, and Alice Coucke. Speaker verification is the task of verifying a user identity based on their voice print. We propose a fixed-size speaker embedding model performed in two stages. In the first stage, a streaming neural network that takes as input an arbitrary long time series of acoustic features and output another time series of higher level features. This part is referred as Sequencewise network. The second stage consists of an aggregator followed by few linear transformation and is called embedding-wise network. It takes the output of the streaming stage along the time dimension to build a fixed size embedding of the audio signal. Let's start with the sequence-wise level. For this purpose, three main families of neural network architecture are used. TDNN stack used in the X vectors, ResNet with two-dimensional convolution, popularized by Voxelab dataset paper releases, LSTM stack, proposed by Google in the paper Generalized End-to-End Loss for Speaker Recognition, and which is mainly used by them to the best of our knowledge. Some recent approaches also try to use multi-scale feature concatenation and self-attention. We propose a residual network architecture with one-dimensional convolution based on the QuartzNet model with few modifications. ReLU is replaced by parametric ReLU to prevent dead neurons as we deepen the network. Max pooling after the first convolution block halves the following layer computational cost. Max feature map as activation inside block reduce the parameterization and allow for deeper network. This was for the sequence-wise part. Now, embedding-wise, we first need to aggregate the time dimension. To this purpose, we select Gauss vector of locally aggregated descriptor that was first proposed by Xie and al. In 2019 for speaker recognition task. It has several benefits. First, it's partially streamable, contrary to attentive pooling, for example. It's explicitly able to reweight from and filter them so that it can completely ignore part of the reference. There is no big channel dimension at input, contrary to, for example, the statistical pooling. And proven performance for this task are observed. Main drawback, though, is that the big last layer reduction is computationally heavy and does not fit our constraint budget. To solve this issue, we proposed a lightweight GVLAD replacing the last projection layer by a weighted mean cluster contribution, come with almost no performance drop, and the cost of adding a new cluster become linear instead of quadratic in the number of learning parameters for the projection layer. We add linear projection and batch normalization after this. The overall is called the embedding-wise part of the network. Let's take a look at the model specification. As you can see, given our constrained budget, we favored deep and narrow architecture. Best performances were obtained with 22-layer deep sequence-wise network. Also, please remark that compared to the GVLAD work from Xie and al. For speaker recognition, we select a higher number of contributing cluster k equal 32. Separating the model in two distinct stages allows to set decoupled memory and latency budgets. Thanks to Tract, our open source neural network inference library, we are able to run the first stage in streaming mode. In this table, we show computation and number of parameters involved in the different stages. To the best of our knowledge, is the first time such a tiny network is proposed for text-independent speaker recognition. While computational resource is essential to know on which device the system can run, latency is the cornerstone to real-time applications. In this table, we report average latency in milliseconds to embed audio with durations of 1, 5, and 10 seconds. Variability observed being below 2%, it has not been reported here. We select two kinds of CPU, an Intel i7, typical of a modern laptop, and a Raspberry Pi 3B, close to what we can find in the IoT industry devices. We use two inference modes, batch, where we apply the whole embedding process once unpointing is triggered, stream, meaning the sequence-wise part is performed in streaming, so that after unpointing, only the embedding-wise part remains to be computed. Partial streaming of the aggregation module is not applied here and should further improve the performance. It's left for future works. As you can see, streaming provides major speedup gain. By example, it embeds 5 seconds of audio segment with below 200 millisecond latency on a single core of Raspberry Pi 3. In order to benchmark the performance of our module, we set few hyperparameters. We then choose to follow two experimental setups. We first benchmark on VoxCeleb, training with VoxCeleb 2 only with no augmentation, and evaluating on VoxCeleb 1 verification test sets. Baseline are the best performing models with the same training and evaluation protocol at various number of learning parameters. Results are displayed in this figure. X-axis showing the number of learning parameters in kilo with a logarithmic scale. Y-axis showing the equaler rate for this task, meaning that the optimal model would be at the bottom left corner. As you can see, we are almost on par with QuartzNet plus GVLAD architecture as it was proposed by Xi and all, with 2 orders of magnitude less number of learning parameters. We also did not report the number of megaflops here, but the difference is often in our favor, meaning that, for example, compared to a solution, the Cheng 2020 paper, shown in this figure, is 6 times bigger in terms of number of learning parameters, but results in a 30 times more CPU operation at processing time. We then check the robustness to noise of such a model. To this purpose, we select Voice Obscured in Complex Environmental Settings 2019 Challenge. We compare to the 2 best team reported. In this experiment, training on VoxCeleb augmented with Muson dataset is performed. We simulate over 5,000 rooms and augment randomly 8 times each original audio sample. As you can observe in this table, on average, we propose a solution which is 26 times smaller in terms of architecture, but showing limited 2.6 absolute increase in terms of equaler rate. To sum up, we proposed a small footprint text-independent speaker verification architecture suited for embedded systems, giving on VoxCeleb 1 verification test set 3.31% of equaler rate and showing competitive results on acoustically challenging benchmark. Our architecture of 247K learning parameter and 11.5 megaflops is composed of a QuartzNet with max feature map and a simplified GVLAD aggregation stage. Computational and latency analysis are provided, highlighting a usefulness of partial streaming for this task. Thank you. If you have any question, I remain at your disposal at julien.balian@sonos.com. Have a nice cast.